Thanks for attending my talk about hybrid neural BRDFs. It's some work I did with Anastasia, Georges, Antoine, Pierre, Damien, and Romain. So the context is about real-time rendering in production. When you think about modern engines, the main thing you think about is rendering quality, and it's a key thing. Modern pipelines, they have real-time ray traced shadows, specular GI, or even volumetric fog. But all of this is mostly based on microfacet-derived models. Such microfacet models, they are interesting for real-time rendering pipelines because they have meaningful parameters. They are very fast to evaluate, and they come with a built-in importance sampling scheme, which is very important, especially when you try to consider ray tracing pipelines with your real-time rendering. However, they suffer from limited expressiveness, which means that sometimes you can run out of things that you can represent, and it can be a bit annoying for artists. So what can we do in production to go above this limitation? We need to have a new appearance model that can represent more complex effects, but we do have some constraints. One constraint is true real time. We want to have very, very low evaluation times, a low memory footprint, because we don't want to render the rendering more heavy, and we want to disrupt the pipeline, the actual rendering computations we do, as little as possible. Here are some alternatives to microfacet model to achieve some more complex effects. So we have specialized models that are also analytical, such as multi-layers, iridescence, rough diffuse, or fabrics. These can all represent such effects with high fidelity, and they also are fast to evaluate. They also sometimes come with important sampling for path tracing and ray tracing. However, they are not very versatile, which means that in a production pipeline, you would end up picking and choosing between many different effects, which can be a bit complicated with the workflows. Recently, we have seen the advent of neural models, especially the model of Zeltner and colleagues that can be used in production pipelines with ray tracing because it's very fast to evaluate. They can fit any BRDF data. However, they are much slower than all of the previous model I considered. And for real production engines, it can be even too much. They lack the meaningful parameters, which means that once you train the model, it can be complicated to explore possible appearances. And importance sampling is a kind of a separate issue. So you need to find either another neural network for importance sampling or a completely different approach. In particular, for production engines, you often end up with multiple samples. So you sample all your lights in your scene, you sample your map, or even GI probes for current video games, which means you end up sampling your BRDF, evaluating your BRDF many times per pixel. So one thing that could be interesting to develop is a way to trade accuracy in your BRDF evaluation for performance when the samples that you would be computing will not contribute much to the final appearance, because not all of these samples contribute equally to the final image. So the idea we present is combining analytical and neural BRDF models, starting with a base appearance from a microfacet-based model, and computing only the residual appearance with a very small neural network. We want to keep the advantages of the analytical model, so intuitive editing, fast evaluation, and important sampling scheme, and have the more complex effects that can be evaluated with this small MLP, limiting the overcosts that we introduce with the neural method. The way we implemented it is as a corrective model over a microfacet model. So we start with a GGX specular lobe and a Lambertian diffuse. Technically, you could choose any kind of base model, depending on your situation, but we choose this one. Then we modulate it with a bounded gate between 0 and 1, and we add a positive corrective term that can modulate the final result. And then we get our complete model that produces better results on complex BRDFs. The two outputs of the gate and the positive correction are produced from a single small neural network. In particular, the GGX and Lambert part provides a fast analytical fallback that can be used for low importance samples, and provides a fallback also for importance sampling when you are using ray tracing or path tracing. The gating term provides a directional attenuation term, which means that when the analytical model overpredicts the energy in a specific pair of directions, this part can reduce the energy. And the positive correction produces effects that are not representable by the analytical base. In practice, this is the architecture we chose. We have per BRDF P vector, which stores the analytical parameters for the model, and a small MLP with two outputs, a sigmoid output for the gating term, and an exponential output for the corrective term. The inputs to the neural network is just the two viewing directions and lighting directions, as well as a non-interpretable latent code that is optimized per BRDF. So we have this shared MLP that is shared for a whole database of BRDFs, so multiple tens of BRDFs. But you could also curate a small collection of BRDFs if you want to concentrate on a particular effect you want to represent with the MLP. So you have your many P and Z vectors that represent each one of your BRDFs that are all sharing the MLP. The MLP itself can be stored with a few kilobytes of memory. In the depicted 32x3 model, it's only 14 kilobytes. And its materials can still be added after training by just freezing the parameters of the multilayer perceptron and optimizing only these two vectors. When we are training our model, we use gradient descent, but I will come back to it later. The loss term, it starts with a loss on the full model, looking at the complete appearance. And then we add another term that supervises only the analytical component. The idea being that we want to enforce division of labor. We want the analytical model to do the heavy lifting of defining what a BRDF is, and the neural model to only do the offset from this model. So when we do not use this second analytical term, we can get into a situation where the analytical model will kind of work to help the complete evaluation, but will not be a good fallback and a good importance sampling on its own. So adding the second term makes it so that the analytical part on its own looks better and therefore will provide a better importance sampling. In the end, we also find that it still helps for the metrics with the full model to add this second loss term. We evaluate our model on three measured BRDF datasets, MERL, RGL, and UTIA, using large batches of bidirections that we sample every single BRDF at once with. We use stochastic gradient descent with the ADAM optimizer and implement everything in PyTorch. And the main evaluation we do is against Zeltner and colleagues as a neural appearance model that is completely neural network based. So the benefits we claim to compare to the fully neural based methods is a reduced neural network size for a given quality target, limited per-material memory, and an analytical fallback that can be selectively evaluated in place of the neural network when needed. Looking at quality with respect to the neural network size, we can see that for a given quality, we can get better results looking at a relative error metric here. And we have a certain gap in quality that reduces with the neural network size. So let's say we want to get this level of quality in this metric. If we project back the neural network size, we can see that for an equivalent error, we can have a much smaller MLP than with a completely neural approach. When looking at rendering quality, but with this time the same MLP, looking at reference for MERL, we get very low error. Our analytical model on its own can get pretty close as well, and we still do better than a fully neural approach. Looking at the more complex BRDF from RGL, our full model is able to do the iridescent part correctly. Of course, the analytical model on its own cannot produce such effects, so it will be quite far, but we'll still get the same energy distribution. And Zeltner on its own is still a bit worse in terms of rendering quality. When working in path tracing, we render a scene here, a demo scene with the BRDFs from every single dataset at once. And we can see what's the effect of disabling the neural network. For example, the fuzz on the couch in the back and the pillows, as well as the iridescent effect on the vases. If we disable completely the neural network, we can get the scene in only 1.1 millisecond per sample, but we'll lose a lot of quality. We can enable the neural network only for the first few bounces, increasing the quality by a wide margin, but still getting a wide acceleration, even with hardware acceleration. And even using a single neural bounce, we can see that everything up to the found bounce looks quite good, but on specular reflections, we can see what is missing. Okay. When implementing our model in a production engine such as the Snowdrop engine, this requires very minimal changes. We just add a gbuffer frame buffer with only the latent vector, and we use the built-in analytical BRDF that is already in the engine. Because the pipeline, the rest of the pipeline is completely unchanged, we can still use every post-processing techniques that already exist, such as denoising, upscaling. In this scene, the neural layer only has 0.3 milliseconds of extra GPU time, and with selective evaluation enabled, as I described before, such as disabling the neural network where it will produce very few energy, we can even reduce it to 0.1 milliseconds. Okay, so once we have trained the network, one advantage of having the analytical underlying part is that we can do edits. So the original appearance looks like this with the analytical model on its own, and like this with the full model. We can decide to edit the analytical parameters, and we get a coherent edited appearance for the full model because it is only kind of a layer part on it. It's also possible to do interpolations between BRDFs that were trained together. So taking two completely different BRDFs from the RGL dataset, we get coherent results between these materials. However, we do not claim that we can edit the latent code on its own, and we can produce unexpected results that break BRDF properties, especially energy conservation when looking at the Z vector on its own. Okay. One limitation of our approach is importance sampling. Because we only use the GGX plus the Lambert model, for some BRDFs that are very far from this model, we can get energy that is missing in some directions or that is over-evaluated, which means that we do not have the most efficient importance sampling by just using the GGX analytical part. Using another example from MERL, we can see that we will not importance sample the grazing angle energy, which will reduce the efficiency of our importance sampling method. Another future work is extension to SVBRDF, such as large shaders that are expensive to evaluate. It can produce very arbitrary appearance. We can try to compress them into a single neural BRDF. This is kind of what Zeltner and colleagues does. But one more interesting evaluation is extension to measured SVBRDFs, because when you measure SVBRDFs from real data, you have much sparser data with noise and incomplete data. So the idea would be to leverage the analytical models that can be optimized with very few parameters to be able to optimize better the SVBRDF with the neural model. One other idea for SVBRDF would be to add the clustering of Z and P vectors so that you can add compression to the algorithm by finding clusters in Z that maybe will not impact much the final appearance overlaid on top of the analytical parts. So to conclude, our take-home message is increased reconstruction quality at a given memory or compute budget. We can exploit the analytical opponent that is already present in the rendering pipelines for importance sampling and addition. And at runtime, you can selectively disable the neural network part of the model to get various performance gains and trade-offs. So thank you, and you can have a QR code to go to see an interactive viewer that sometimes works on mobile if you have a recent phone as well. Thank you.
Sure. There's a lot of time for questions. The first one would be over here.
Thank you for the great presentation. I have a question about the edition you showed at the end when you changed the color of the car. Yes. Since if I understood correctly, the neural part is just a fine modification of the base, so you multiply by something and then you add something. Yes. So that means that the correction is going to have maybe the wrong color when you change the base.
Yes, that's one of the limitations of the edition, yes.
And I was wondering if how expensive it would be to have a nonlinear dependence on the base model, so that the so that you don't have to retrain when you do this kind of editing?
Yeah, so what you're saying is that when you edit, you don't really change the additive part of like the neural part, so you can get a weird appearance if you change the analytical part too much. Yes. One thing we tried to get above this was inputting back the analytical parameters back into the neural network, but it gave a kind of limited results in this case, and it would increase a bit the size of the neural network to be able to handle the more diverse inputs. And also because then when you edit, you could have defined unseen data during training. You would need to have some more training data to go with it, so maybe have synthetic data to kind of supervise the addition as well. That's something we haven't been able to try yet. But yeah, addition is a thing we need to supervise directly. It's not the case yet.
Okay, thank you. And just a tiny question. How long is the training? Like, are we talking seconds, minutes, hours?
A few minutes. On 150 BRDFs, it's about 10 minutes max on a good GPU.
Okay, thank you.
There's ample of time for further questions. One is down there, behind you, where Carol is. There. Well, he was more lucky.
Hi, thanks for the nice talk. I was wondering how you compare results to Zeltner's results, because there's no open implementation, right?
We re-implemented the neural BRDF part of their model only, not the spatially varying part. So yeah, like taking instruction from the paper, basically, we implemented it and we found similar results. So yeah.
Thanks.
There's one more question there.
A nice presentation. I was wondering, is there a way after your pipeline to ensure things like energy conservation?
So we do not supervise energy conservation directly. However, because we just like have it as a metric, and we find that it's pretty good on the medials that are parts of the data. If you do edits that reduce the energy, then you will be fine. However, if you do large edits that can add energy to the BRDF, you can get in trouble if you had already a very high energy BRDF. But most of the time it's completely fine, and you can try it yourself in the viewer, editing the parameters. Most of the time you are fine. The only thing that I saw that can get very wrong with the energy is when touching the latent vector after training, because we don't really have a supervised training for that.
Thank you.
I would have a final question. Can you pull up the architecture slide?
Yes.
Not really question, question maybe. It's more about how you combine all those things. So it really takes outgoing and incoming and so forth. What does it do, the neural network, if it does this, right? It has to transform it eventually to some spaces. And I want to make people aware there has been this paper that took all kinds of internal states of an existing shader and ran a neural network training on that. So the dot product of half vector and normal or something. It's an internal state of a shader. So what made you choose, why is it multiplied and added? He said it very nicely, a fine combination, but there's millions of other combinations. Will this be explored by somebody one day, or would you do it? Or?
You mean about a way to combine the neural network outputs, or about the inputs?
How all this stuff is combined, right? Yeah. FA does some stuff. It does a dot product between the half vector and the normal, and it's an intermediate result. What stops you from passing this on to the other network? That
we tried various inputs that to handle the directional inputs. So converting in like Ryuzinkiewicz coordinates, converting in various coordinates, but we did not find increased results with them. And in fact, the ones that work best were just putting the raw Cartesian values of omega and omega as in inputs that work best.
Yeah, maybe worth reporting. Sometimes people don't report. Do you write it in the paper that you tried?
Yeah.
Okay, then
this one I should read more carefully. I don't know. There are some ablations in the paper.
For me, this is useful information. Okay, we're out of time. We move to the next session. Let's thank the speaker again.